So what's the matter? Is one of the cleverly named titles I have for my notes. And you guys don't have to take this down. You guys can, thank you. You guys can watch it. You guys can take down what you want. I'll post it right after class on the website. So we're going to define matter. This is designed so that you guys know that all matter has mass and volume. To determine if something is or isn't matter, and use the terms mass and volume appropriately and understand them. And I'm sure you guys have already done this, but appropriately measure mass and volume. You guys all measured mass in biology, or before that, all measured the volume of a liquid. Good. I mean, if you've done a recipe, measured half a cup of oil, that's measuring volume. Or, sorry, I should probably say 250 milliliters. Sorry, I used imperial units. We did this. So matter is anything with mass and volume. Mass is a measure of how much matter is present. And mass is absolute, meaning that if you have no matter, listen up, guys, you have zero mass. And the more mass you have, the more matter you have, the more mass it has. Volume is also absolute, and it measures how much space the matter occupies. Things that aren't absolute is something like degrees Celsius. It's relative to something. So 0 degrees Celsius doesn't mean you have zero energy. It just happens to be the temperature at which water freezes. It's relative to water. And 100 degrees Celsius is the boiling point, so it's relative. Like an angle is not absolute. It's relative to each other, to the two line segments or rays which go through there. As talked about that in biology. So that's why, and we're going to talk about absolute temperature as we move on. You guys might have read it in your book. I think they talked a little bit about Kelvin. Yep, they mentioned it. That's absolute temperature, so it's no degrees. The units we use in measuring mass are grams. That's the SI unit. System International, SI. They are the organization that's responsible for units. And which is good, because way back in the day, imperial units, well, they sucked. Because, well, when the king changed, the foot changed. You know, when you're measuring your horse in hands, well, if you had a real person with really small hands, you're going to have a really tall horse. I guess. I don't know. So they really are relative. But, well, science, what they want to do is make things replicable and consistent. So that's why they actually have an actual kilogram. So they have what a kilogram is defined as. And actually, interestingly enough, they're trying to change what that is, and they're trying to make it a certain number of carbon-12 atoms so that it can be more consistent. Liters are the SI unit of volume, or centimeters cubed. A milliliter is the same thing as a centimeter cubed. If you guys ever heard like a doctor show, if you're watching ER or House, you might hear something like Dr. House be like, give him 12 cc's of Benadryl. That's just 12 cubic centimeters, 12 milliliters. That's what it is. That was my house impression. I know it's terrible. Matter tree. So this is extended. Matter can be a pure substance or a mixture. Pure substances, you can be an element if you're one atom, group 1. Compound, group 2, if you're made of more than one type of atom. Type of atom, not atoms in general. Okay? Mixture can be homogeneous, which is also called a solution. Okay? Not like the solution to an equation. But a solution is a mixture of evenly distributed particles, more than one type. Like, for instance, my favorite solution is the air. Don't forget that. Because I breathe in air and it keeps me alive. Air is a mixture of basically nitrogen and oxygen. So it's 78% nitrogen, 21% oxygen, 1% carbon dioxide, argon, and other stuff. But it's a solution. Salt water is a solution of salt mixed with water. You can have a solution of metals too. You can have a solid solution, like brass. Or an alloy. Alloy is just a mixture of metals. So they're evenly distributed all throughout. Like I can't send Dennis to the part of the room with no oxygen, can I? That would be a horrible punishment. Like, go over there where there's no oxygen. Can't do that because oxygen is evenly mixed throughout. And they have to be separated in different ways. Heterogeneous mixtures are unevenly mixed things. Like homogeneous mixture solutions, that was group 3. Group 4, heterogeneous mixtures. You're a heterogeneous mixture. You guys are heterogeneous mixtures. They have their different parts. You can see them differently. Sometimes you can see them, sometimes you can't. Like milk, you really can't see the separate parts. Blood, you really can't see the separate parts. But they're heterogeneous mixtures. Okay? Sorry, I put this slide in the wrong place. A colloid is a type of heterogeneous mixture, like fog. You have your very tiny, tiny, tiny particles of water. They're clumped together, and they're in the air. So when you have your fog, that's why you can't see through the fog, because they're small particles blocking the light. So, and same thing with if you had muddy water. Muddy water would be a heterogeneous mixture because you have the small mud particles, the dirt particles mixed all throughout the water, but you have your dirt part and you have your water part. And if you have the Tyndall effect, I'm not going to testing this, but you might hear about it in the SATs or in physics. If you have a homogeneous mixture, a light beam, you will not be able to see the beam of the laser. In a heterogeneous mixture, or a colloid, you will be able to see that beam. So if you can imagine if you had smokes, and you had shown a laser through smoke, you'd be able to see the laser. Whereas through air, hold on, I have a laser. So do you see the laser in there, through the air? No. Let's see. I can't really make off the top of my head. I don't have anything. I can't make any fog. I don't have a fog machine on me. I should get one. So, and it's too warm for me to create fog with my breath. So, but you'd take a look. Hopefully, you guys can see that. If you can't see it very well, take a look on the video. Because you can actually see the laser beam through the muddy water. Okay? And the reason is the small, tiny particles that they reflect the light. So they bounce off, and then that's why we can see them. Okay? Phases of matter. You guys have all talked about these, but solids, what they have is they have a definite shape and a definite volume. They can hold whatever shape they're in, and their volume doesn't change. Liquids, they have a definite volume. They take up a certain amount of space. Thank you. So there's a certain volume of water in here, but however I move the container, that's what the shape becomes. So the shape changes readily with whatever is holding the water. We'll talk more about liquids and solids and why we have these different phases. Gases are awesome. Gas laws are one of my favorite topics to study and teach. And we're going to do that. I believe that's third term. Maybe second or third term? Can't remember if it's end of second term or beginning of third. But it's a really, really interesting topic. So gases are amazing. Gases occupy an undefined amount of space. So whatever container they're in, they're going to occupy that entire container. They don't even have a shape. They can be compressed into whatever shape they are. They have a shape of whatever space they're in. So if you have a vacuum is a part is an area with no matter in it. A lot outer space is pretty much a vacuum. Has a very low pressure gas, very, very low. And if you let a gas go in a vacuum, it'll occupy that entire space. Okay, it'll expand to fit its container, and you can compress it too. And we're going to talk all about that and why. And a plasma, we don't have too much of that naturally in Earth. You see plasma in lightning, in neon lights. You have a high energy ionized gas. That's why the neon lights give off a certain color, because they have a high energy and they emit light at a certain wavelength, which is determined by color. We'll talk a little bit about that. Yes, Aaron?
Is Aurora Borealis an example?
I don't know. I don't think so.
No, it's like
Yeah.
Like
Yeah, I'm pretty sure it's not, but thank you, Shelby. So, you find it on the sun. So if you're on the sun, before you're vaporized instantly, there'd be a lot of plasma there. You'd be like, wow, plasma, gone. Here's some models. Misconception, guys, and I'm going to break this misconception. Particles in a solid are moving. They're just vibrating in place. I like to think about the phases of matter, like being on the train right after the Red Sox game. So if you're taking the D line from after a Red Sox game from Kenmore Square out to Riverside, like to Wellesley. I think it's Wellesley or is it Newton? I don't remember. But anyway, right as you get out of the game, you're going to get on this Green Line train, and everybody is going to be packed like this. They can still move, but they really can't move very much. As you go further out, it becomes more like a liquid, and you can kind of circulate and kind of push people out of the way to get to the train. And by the time you get to Riverside Station, you could probably run and do cartwheels and do some subway performing if you wanted to. That would be like a gas because there's not many people there. It's so empty. You have the whole car to jump around, and it's better than being packed tightly and it smells terrible. So gases matter. I know it blew society's mind in the 1800s. They're like, gas isn't stuff. They didn't know it existed because it's pretty abstract. You're surrounded by all these particles that you can't see, and it's one of the big things about how chemistry, started. We can't see things. We can't see gas particles. We can't see atoms. What we do is we rely on evidence. If you've ever felt this phenomena of differential pressures in the air, aka wind, that's air moving. That's air particles hitting you. Like if you get wind in your face, that's a bunch of air particles hitting you in the face. You just don't notice it because you're used to it. What Priestley did is he was in the late 1700s. He studied matter. He studied chemistry, and he was also a minister. Interestingly enough, and what he did was he filled up pig bladders for gas storage, effectively inventing the whoopee cushion. So he was one of the early scientists that worked on convincing people that gas is matter, and it's all relative to energy within the same substance. The lowest energy phase you're going to have is your solid. As you increase your energy, the particles move around more. They can break some of those bonds between them, and they form a liquid. Higher energy, even more, and these are our normal phases, solid, liquid, and gas. That's what we're going to be talking about in chemistry almost exclusively. As you increase the energy even more, the particles can break that, what they call IMF, the force holding the particles together, and become a gas. Okay? And plasma is that high energy. You toss like an electric current through neon or argon. Get through that electron, it's like, good job, guys. Don't forget to scourge your Chris.
And isn't that also that really